Scikit-learn is a set of machine learning tools in Python that provides easy-to-use interfaces for building predictive models. In a previous episode with Per Harald Borgen about machine learning for sales, Per illustrated how easy it is to get up and running and productive with Scikit-learn, even if you're not a machine learning expert. That episode about machine learning for sales really sparked my interest in Scikit-learn and made me understand just how big machine learning is getting, partly because the interfaces for doing machine learning have gotten so easy to use, so self-serve. And today's episode, we go deeper on Scikit-learn. Srini Kadamati hosts today's show, and he interviews Andreas Mueller, who is a core committer to Scikit-learn. Srini and Andreas discuss the background and implementation of Scikit-learn, and they walk through some prototypical workflows for using it. We will continue to do shows about machine learning, and as always, send me an email with any of your recommended topics and any other feedback you have on the show. Thanks for listening. Continuous integration is so useful that I've started using it on my own personal projects. SnapCI from Thoughtworks has the fastest setup I've ever seen. I registered for SnapCI with my GitHub account, and after a few clicks, I had continuous integration pipelines set up for a Node.js application and a Rails application that were just sitting on my GitHub account. And I don't want my users to experience breaking changes, so I want to run a large suite of tests for my application every time I push a change. And SnapCI will run those tests quickly, in parallel, on a worker that SnapCI spins up and takes care of for me. Whether you have personal projects like me, or you work at a company that is looking for the perfect tool to improve the deployment process, go to snap.ci/softwareengineeringdaily. SnapCI embodies the lessons that Thoughtworks has learned from 20 years of software deployment, the same lessons that have been written about by Martin Fowler and Jez Humble. Check it out at snap.ci/softwareengineeringdaily. It would support Software Engineering Daily, and you would get to check out continuous deployment. snap.ci/softwareengineeringdaily. Thanks for listening.
What is the goal of the Scikit-learn project?
So I can speak from my own perspective. So we don't have like a board or anything, and so we don't have like one entity. But so for me, the goal of Scikit-learn is to make machine learning very easy to use and accessible so that a lot of people can use it for their problems. We put a lot of emphasis on ease of use, on documentation, on a simple API, so that scientists from all kinds of fields or people that work in companies can really easily pick up machine learning and apply it for their problems.
Makes sense. So what were people using before Scikit-learn, and how does Scikit-learn address some of those pitfalls?
So it depends a little bit on the community. Some people were using R, some people were using Matlab, some people were just using like C++ stuff. It's if you're doing research with C++ or data science with C++, you're really, really slow. Even though the code runs very fast, every time you need to set up a new experiment, you need to like read it in a new file, compile with the new file name, whatever. And every time you want to show an image, you need to write code to show the image, and it's really, really slow. And so that's not a great environment for interacting very quickly with your data. In Python and R, there were both things before Scikit-learn, but they were not as comprehensive, I think. I know there was PyBrain, which is pretty old. Right. There was MVDP, I think. But yeah, a lot of the stuff that Scikit-learn added to what was there in Python was, I think, that it was comprehensive. And particularly it had bindings to liblinear and libsvm, which was very important for people. And then at some point we got random forests, and then basically everybody started using it.
Right. That makes sense. Yeah, I definitely, I use, as I mentioned before, I use Scikit-learn on a weekly basis. I think the API is definitely the best part. I mean, with just 3 lines of code, I can kind of run and test almost all of the major machine learning models, which is really, really quite impressive. So how is this achieved? Do you have a really simple structure? You have a really simple API. What is, do you guys assume a standard set of input when you're training a model? How does Scikit-learn represent the model? So let's start there.
So one of the things we achieve being sort of very simple is that we use very few types. So basically the data is always a NumPy array, and basically all models assume that it's a float array, and basically that all the data is just continuous features. In some sense that's kind of limiting because we have a little bit some issues with like how to represent missing data or how to represent categorical features. When we started Scikit-learn, there was no pandas, so and that was also not really the goal. So most scientists work with like just float data, and so this is our data representation. There's no class called data; you just give it a NumPy array. That makes it very easy to integrate it in other tools. I remember that there are some other machine learning libraries that have a data class, and that immediately puts some barrier between a user who wants to get stuff done and doesn't use whatever class you defined and the library. So we want to make sure that there's as few types as possible, so there's sort of as few things as possible that the user needs to learn about before they can use the tool.
No, that makes sense. What do you think are the limitations of just taking in a matrix 2-day array for most of the methods?
I think for most of the methods, actually not a problem. It definitely limits what we can do in terms of the interface, so it's very tricky to do collaborative filtering with this interface. It's like recommendation systems. It's also, you can't really do reinforcement learning with this interface. But this is basically things we said this is out of scope, and if you want to address these, you need a much more complicated interface, or at least a different interface. In terms of data, I mean, you can also not really do time series because time series have different length and so on, and so you can't really represent them as one homogeneous array. And then types obviously are kind of tricky. That's not really a problem for most machine learning models. Most machine learning models only operate on floating point numbers. So it's more a usability thing. So in R, a lot of the models automatically convert your data into some format that can be consumed by the model. Scikit-learn is very explicit, so you need to say explicitly what do you want to do, and Scikit-learn doesn't do any kind of magic to transform your data.
No, that makes sense. Interesting.
So maybe one thing that I should add is there's for tree-based models, it actually would make sense to have categorical data types.
Right.
And we're working on this, but it's kind of tricky because of the data structures we're using. It's tricky to have a categorical column in the NumPy array, so we need to add some additional mask that says these columns are categorical.
Interesting. So do you think that's going to affect performance, or is that just a trade-off that you guys are willing to make with the masking process?
I don't think it's going to affect performance. No, it's more like it's not the nicest data structure because you have to pass in two different objects. They're not coupled. But I don't think in terms of performance it's worse. I mean, it's not. Maybe in terms of I guess inefficiencies for the splits it could be worse because we're using float to represent integers. But I don't think it's going to be an issue.
Okay, interesting. So you actually gave a talk at the 2016 Data Science Summit where you discussed in depth the principles that really drive the development and maintenance of Scikit-learn. Could you give us an overview of those principles for listeners who haven't seen the talk?
Now I need to remember a talk that I did like a month ago. That's tricky. So it's really, I mean, one of the things I mentioned already is I actually mentioned multiple of them already. It's focus on documentation, focus on ease of use, focus on consistency of interfaces. don't create complicated class hierarchies. So basically, there's two important pieces that you need to know about in Scikit-learn. One is what we call the estimator, which is the model, and they all have the same interface. They all have a fit method, and they either have a predict method or a transform method. And sort of if you know these three methods, you can do most of the stuff. And then there's NumPy arrays, and all the data is in NumPy arrays. And so you have very few things that you need to worry about. Then in terms of consistency, not only all of the models have the same interface, but also grid search looks like a model, for example. And pipelining multiple steps together also creates a model again. So everything is like pretty uniform.
Right.
Then other important things are, I guess, like we make sure that API is compatible. I'm not sure if I talked about this in the Data Science Summit talk, but we make sure that we don't break anything between versions. We write a lot of documentation. We write a lot of testing. We have code that tests if the error messages are good. When people give like misshaped input. Yeah, I don't know. I think these are like the main points. It's really keeps some things simple, and in particular, not only for the users but also for the maintainers, because it's an open source project, and so you can't just tell someone, here, deal with all this legacy code, which is what people in companies do all the time. You can't really hire people for open source project, and if you want people to keep maintaining it, then you need to make it easy to contribute, and you make it easy to maintain. Otherwise, people will just abandon it.
Yeah, no, makes sense. That's interesting. So give us a sense of the kind of end-to-end workflow. So you have a data set. Your goal at Scikit-learn is to make it as easy to use as possible. So how would, for people who don't do machine learning on a day-to-day basis, what does the workflow look like for a really simple model? Starting with a data set. Yeah.
So first I'll give you the simple answer, and then I'll give you the complicated answer. So the simple answer is, let's say you want to do supervised task like classification. Simplest case, you have two classes. You want to say, for each data point, does it belong to class A or class B? So then you have a NumPy array that represents your data. Like each row in the data set is one data point. Each column is one feature, one thing that describes this data point. Then you have a vector of responses, or class labels in this case, that says for the training data that you have collected, these points belong to class A, these points belong to class B. And you want to use this training data, where you know the answers, to build a machine learning model. So the first thing that you do is you split your data into a training part, which you use to build the model, and a test part, which you use to validate the model. If you just used all your data to train the model, you wouldn't be able to say afterwards whether your model is any good or not. So you need to hold out some data, pretend you don't see it, and this stands into future data to which you want to apply the model. So usually you want to put this model into production in your company, whatever, and you want to make sure, or you want to at least know how well will it perform. And so the test data is to give you some estimate of how well it will perform. Okay, so you split the data. Now you pick a model. Say you pick a random forest classifier because your friends talk about them all the time. You instantiate the class. So you import it, you instantiate the class, and then you call the fit method with the data as one parameter and the labels as another parameter. And that basically builds the model. The fit method is sort of where all the learning happens. And then the model will be stored in the object you instantiated. So the random forest object you instantiated will contain the model. And if you want to make predictions, you can call the predict function on any data. So on the training data, for example, or on the test data. And the predict function, predict method will return class labels according to what the model thinks. Then there's also a score function, or score method. I always say function when it's a method. The score method, and which will compute how well you're doing. So you can call the score method on the test data that you held out, and you'll know how well does your model do.
Software engineers are always looking to automate their work. Software automation lets us get more done with the same number of resources. Investment automation works the same way. Wealthfront is an automated investment service that relies solely on software to acquire and manage client accounts. Traditional investment services have many humans in the loop, advising clients and taking fees. The problem with these older advisory services is that the advice that these services are applying is often so systematic that a computer could give the same answer, or an even better answer. Wealthfront takes a new approach with software-driven automated investment that provides better returns through software engineering. Go to wealthfront.com/SE daily to get a special offer for our listeners. $15,000 managed for free when you open your account. Don't pay commissions and account fees. Maximize your gains with Wealthfront's set it and forget it investment automation. Check out wealthfront.com/SE daily. It would support Software Engineering Daily, and it would also introduce you to the world of automated investment, so you can see if you like it or not. Wealthfront.com/SE daily. Thanks to Wealthfront for sponsoring the show. You've been a loyal sponsor, and we really appreciate it. Now let's get on with the show.
So in this case, random forest for classification, for people who are new to the problem, what kinds of things should they watch out for? Obviously, people talk about overfitting a lot of time. They talk about different kinds of classification accuracy measures. So how should someone think about that problem?
So I guess in particular for random forest, and all the models have a lot of parameters to tune, and I don't want to go into details here, but for random forest, you need to make sure that you have enough trees in the forest. There's a parameter called an estimator. The larger you set it, the better it will get, and but the slower it will get too. Like it will linearly get slower, and so you need to set it high enough to get a good result in your test set, but you don't want to wait forever. And also, it consumes more memory. But other than that, random forests are pretty hands off, and they'll just work. In terms of metrics, most problems in the real world are imbalanced. So often you have like 99% of the data is in class A and 1% is in class B. And if you use the default metric, which is accuracy, then saying always class A will give you 99% accurate results.
Right.
And that's not very helpful. So if you have very imbalanced classes, you should look at other metrics, and you need to think about really what is it that you want, what's important. Do you want to find the 1%? How bad is it if you get some of the other ones in there?
Right.
I usually like to use the AUC metric, area under the ROC curve, but there's more general measure that works quite well for imbalanced classes. Mm-hmm. But you should really need to think about, what do you care about? It's the same even if you have balanced classes, but then it's not as obvious. But accuracy, like the fraction of correctly classified points, is rarely what you care about. Usually you care about something else, and you should think about more what you actually care about.
Yeah, no, it makes sense. I think the classic example is like predicting default rates on lending data, where 95% are just fine. The data shows that they paid it off on time, but 5% shows that they defaulted on the loan. And so it's like, I think what you're talking about specifically is that if you train a really powerful model like random forest or even logistic regression, then the model will be biased towards just predicting, hey, this guy is not going to default on his loan because that's 95%. 95% of the time, that's what happens. And so if you just use accuracy, then you'll get a skewed idea. That's interesting. So what does the roadmap look like for making scikit-learn work on larger data sets?
Depends on who you ask a little bit, but so I think we should focus mostly on streaming stuff. So out of core learning, there's already a partial fit method in a lot of the for a lot of the models. We don't have it for tree-based models yet, and that's kind of tricky. You probably need a different kind of tree. Like you could implement the Mondrian forests. That might be a thing. But so I don't think we should try too hard to make scikit-learn parallelize over a cluster, because that's not really. I mean, everything is built on NumPy, around the NumPy array, and if you now replace this with some other data structure like a RED that lives on a cluster, then like none of this is going to work anymore. And so maybe it would be better to write a lot of it like from scratch.
Right.
At least the algorithms, because you really have to do quite different things if you want to do an algorithm data parallel than what we did in scikit-learn.
Makes sense. Are there any efforts? I think you mentioned one in the talk. Are there any efforts to make scikit-learn like that simple API work on something like Spark or another tool?
Well, yeah, it depends a little bit on what you mean. So you can run the stuff that's embarrassingly parallel on Spark relatively easily. And there's the Spark Scikit-learn that's actually done by the Spark guys, and basically allows you to run grid search over a Spark cluster. But that means like each model individually is built on a single machine. If you want to do something more distributed, you have to use MLlib. And I don't think there's a particular reason why they wouldn't implement the same interface as we did. I mean, maybe I'm not too closely familiar with their design process, but basically they re-implement the algorithms, and that's maybe what you want to do.
Yeah, makes sense. Interesting. So in the talk, you briefly touched on automatic machine learning and black box model optimization. So what is the difference between kind of a highly interpretable model that's maybe linear regression or something like that, and kind of this black box model? So let's start with those two different concepts.
Well, I guess linear regression is something that a human can somewhat interpret, and you can write down a formula, and you can sort of communicate it, and you can probably write it down on paper, depending on how many features you have. And you at least sort of know, well, if this part changes, what is the answer going to be? How's the answer going to change depending on the inputs? If you have a more complex model like a random forest or a neural network, then this is a lot trickier. Like for a random forest, if you say, oh, I changed this input, what will the output be? Like the computer can compute it, obviously, but you can't really write down a large random forest on a piece of paper. There's going to be thousands of trees, and or at least a couple of hundred, and a human can't really comprehend that.
Right.
If you do more automated machine learning, like the way you win competitions or get really good results, if you average the results of multiple of these very complex models. And so then that becomes even less interpretable.
Right. Makes sense. So it seems like what you're talking about is ensembling models.
Yeah.
So what support does scikit-learn have for ensembling?
Well, there's a bagging classifier, which allows you to do arbitrary bagging. I mean, the random forest and gradient boosting are particular kinds of ensemble. And there's a voting classifier, which allows you to do basically averaging of multiple models.
Interesting. So, going back to what I mentioned about automatic machine learning, what excites you about automatic machine learning, and what kinds of things do you guys want to add to scikit-learn to help with that?
So the thing that we're probably going to add in the short term is Bayesian optimization for not grid search, but parameter search. And we're probably also going to add something where you can search over the steps of a pipeline, which you can't do currently. And so why am I excited? Because at least for the machine learner, the machine learning people spend a lot of time trying out different algorithms and different models and different parameter settings, and to spend a lot of time tuning the model. And that's something I think that can be automated, and I think people can do better stuff with their time. So if we can have the algorithms do that, then we don't need to waste our own time with searching a very large search space. And we can focus more on the problem definition or what kind of features to use.
Makes sense. Makes sense. So I actually spoke with Peter Wang from Continuum Analytics a few weeks ago, and he actually really embraced the fact that the SciPy stack allows data scientists to use the high-level interface of Python with the internal performance optimizations of something like C. In your talk, you actually mentioned the two-language problem and how the separation makes it harder for someone to switch from being a user of Scikit-learn, for example, to being a contributor. So what are your thoughts on something like Julia, which is trying to kind of do all that in one language?
So some of my formulation about the two-language problem actually comes from a talk by my colleague Stefan Kapinski. I don't know if you know him. He's one of the creators of Julia. But I think he really makes a great point there, and I found this quite a problem in practice. Found even a problem for myself. I can write Python and C, but I need to change the tool chain. I can't really debug as easily anymore, and then you need to do CGDB to step down in some weird segfaults. And I hoped we left that behind a while ago, but we didn't. So I'm not sure if Julia is the solution. Julia is definitely interesting. I haven't used it that much myself. So I can't really comment too much on the language. It seems to be very targeted towards scientific computing and less of a general purpose programming language. And I think that means it will always be sort of niche. So it's maybe a good replacement for MATLAB, and I think it was sort of meant as that in some sense.
Okay.
It looks exactly like MATLAB if you've looked at it. But Python has the benefit of being like a general purpose programming language, so a lot of people already know Python even if they don't do data analysis, data processing.
Right.
And so that makes the community a lot bigger, I think, and it makes it much easier for people to get into the community because it's a much more general purpose programming language.
Makes sense. Interesting. Makes sense. Is that something you've ever been interested in? Trying to create a new language or a new framework completely that is kind of a full stack data science language?
I find it very fascinating. I'm very interested in discussion about new Python compilers. There's now a list on Python compilers that is done by Nathaniel Smith, one of the NumPy developers. And so the thing is, creating a new language is tricky because you need to move everybody to the new language. And I'm pretty sure I'm worse at programming languages than all of the Julia developers. And so I don't think I'm a good person to create a new language. I thought about, should we all move to Julia? And it doesn't seem to be happening right now. I can't really say why it's not happening. And so, you can use all of R and all of Python from Julia, but people still prefer to write Python. And I think one of the things is that Julia makes it easier for the developers in a sense, but I'm not sure how much easier it makes for the users. In the SciPy stack, there's a lot of people that just use the stuff, and so they actually don't care about developing. And the algorithms in Python are already fast enough because someone put in the effort to implement them in C. And so the pain point is with the people that implement and not with the people that use. And so maybe there's no motivation for people to move away from Python. I don't know.
I see. Yeah, that's interesting. That's actually a really good point. Cool. Actually, so we can start to close off the interview. So what excites you about the future of Scikit-learn? What kinds of, you mentioned in the talk that you wanted to add feature name support, and, what in general, what kinds of things really excite you about kind of the next 3 years of Scikit-learn?
I think I want to focus a lot more on interpretability and even more intuitive use. And so in particular, addressing more the needs of the data science community. Scikit-learn was developed very much with machine learning researchers in mind and with scientific applications, and it really has quite different demands than what a data scientist needs.
Interesting. Yeah. Do you have any kind of specific examples that excite you?
I mean, they're all boring. I'm excited about the boring stuff. So, I mean, like the feature name support, having things that are more easily work with categorical variables, like better pre-processing, better imputation of missing values, and sort of more automation, and also more ability to introspect. So currently, it's kind of hard to visualize a lot of the stuff.
Right.
Oh, actually, this is like this. I haven't mentioned that anywhere else because it's very new. We're gonna include some plotting code into Scikit-learn. So Scikit-learn so far has stayed away from plotting, but I complained enough so that we're now going to include some plotting code so that it makes it easier for people to interact and visualize the models.
Interesting. So yeah, I think you may have mentioned this when you gave the talk actually. But so does that mean like creating interfacing with Matplotlib to create charts, or like yes. what does that entail? Okay.
It's basically, yeah. I guess in the talk I mentioned it would be cool if we had this, but we're actually going to put it into the Scikit-learn package. So when I gave the talk, I thought I'm going to have to create my own package, but we're going to put it in Scikit-learn now.
Sure. Nice.
Yeah, basically it's writing the Matplotlib code you need to plot the confusion matrix once and for all, so you can visualize it easily.
Right. Yeah.
And and for learning curves, and for plotting the results of grid searches, and for plotting coefficients of models, and so on.
Interesting. Cool. So the last question I have for you is, obviously, you're a maintainer of Scikit-learn. So how can people who are using Scikit-learn for the first time contribute back to the open source project itself?
So we actually have a very elaborate contributors guide. So if you go to documentation and then development, it'll tell you all about how you can contribute to the project. And so I always say the requirement to contributing to the project is you either need to be able to speak Python or English, then you're good. The best thing is look at issues in the issue tracker. There are some that are marked as easy issues, and these should all be able. You should be able to address these. And the main thing about these easy issues is they might not be super impressive, but they get you started with the workflow.
Right, yeah.
And so, how do you set up all the Git branches? How do you push and pull and whatever? How does the review workflow work? What happens with the continuous integration and so on? And so once you got one of these easy issues in and you have some code in Scikit-learn, you can be proud, and then you can start to address some more interesting problems.
Makes sense. Interesting. That's pretty great. Awesome. Well, thanks for coming on the show, and I hope you enjoy the rest of your day.
Yeah, you too. Thanks.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks again, Symphono.
Wow.